Okay, and welcome to another module of Pic16F877. Today we will study about the PWM mode, and to generate this signal we have two pins, the pin 16 and the pin 17 here with the simple CCP1 and CCP2. So that means we have to enable this mode. And what is the CCP module? The CCP module is comprised of three modules: this is capture, compare, and PWM. And the capture is to provide access the current state of the register, which constantly changes its value. So that means you can read the timer one example. You can read the timer one register value anytime. And in the compare mode, this means you can compare the value with the timer one register to trigger an external event. And another PWM mode, this is pull wide modulations. Here we can generate a signal with varying frequency and duty cycle on two pin 16 and pin 17. And the pin 16F877 have two pin, have two module. This is CCP1 and CCP2. And now we discuss about the module CCP1. And what is the PWM mode? Here the PWM mode, you can see it can generate a pulse with varying the periods and the frequency. So in this case example on the slide, you can see that with the same periods, here with the same periods, okay, the same periods here. If the duty cycle of the high is bigger, so the lamp will brighter, okay. And if you can, that means you can adjust the brightness of the lamp according to the high value and the low value. So as I said before, we can generate the PWM signal on the pin 16 and pin 17. So we can generate the signal output here. Okay, so to generate the PWM output signal, we have to concentrate on some special function register. The first one is the PR2 register. Okay, so from the figure A4 here, we know that the PR2 register will be the periods for the PWM signal. Okay, so and another is for the duty cycle. So we have to give the value to the CCPR1L register, and remember that the PR2 signal will be 8-bit signal, so this is a maximum 8255 here. But the CCPR1L here is about 10-bit, because this is have the 8-bit and 2-bit from CCP1 CON 5, 5, and 4. Okay, so this is the 10-bit signal, okay. However, we use the timer 2 to generate the signal, so the timer 2 is the 8-bit signal, and so we will make the timer 2 become the 10-bit signal by set the bit here. Okay, by set the bit here. Okay, so if we set the bit here is 1100, that means the prescaler is 1, and then it will connect with the 2-bit prescaler to become the 10-bit register. So now the timer 2 will be 10-bit register, but remember that when it's compared with the PR2 signal, just compare 8 bits, but when it's compared to the CCBR1H here, it will become 10 bit. Okay, so let's have a look how this flow chart works. Okay, let's have a look. And the diagram will work like this. The first is this one. Example, we are at this point. So at this point, that means the TMR2, the timer 2, will increase and equal to PR2 value. Example, is equal to 255, something like that. So at that time the timer 2 will be clear and then will return to 0. So at this one, it will be 0. This will be 0. Okay, and then the timer 2 will increase, and then the timer 2 will increase when the timer 2 equal to PR2 here, the comparator here, it will load the signal from this register to this register. Okay, and then the timer 2 will increase until it equal to CCBR1H here. So it will increase until it's equal to this register, and then when it equal to this register, the pin RC2 here will become low, right? And now the timer 2 here, 10 bit, it will become 8 bit, and it will continue to run until it meets the PR2 here. And then when it meets the PR2 here, equal to PR2 here, the value will go high again, and then the timer will become 0 again, and then the loop, another loop continuing. Okay, so this is the flow chart of working. And okay, let's go to the next more complicated example. In this example, we want to generate PWM signal with frequency about 19.5 kilohertz. Okay, and the height is the duty cycle is about 70%. Okay, so that means we will have 70% high and 30% low. Okay, and let's calculate. Example, we have the frequency is 19.5 kilohertz, so we will have the T is about 51 microsecond. Okay, 51 microsecond. So 51 microsecond, and to generate a period with 51 microseconds, so how many we have to give to PR2? Because PR2 is equal to timer 2, right? Compare with timer 2. So example, we use our peak is the crystal of our bit is 20 megahertz. So to make the timer go to 51 microseconds, so we have to give the timer 2 how much will it count to. So we have to because timer 2 equal count from 0 to 1, it takes 0.2 seconds, right? 0.2 seconds. So if we have 51 microseconds, so it will count to how much? 255. Okay, 255. So we will give the PR2 is 255. Okay. And now how many do we have to give to the duty cycle? That means we have to give to this one CCPR1L and CCP con 4. Okay, let's calculate. Okay, so when timer 2, please remember that when timer 2 compare with CCPR1L here, CCPR1L load to CCPR1H here, so actually timer 2 will compare with CCPR1H here. The timer 2 here will become 10 bit, okay, 10 bit, and the number of bit here, the number here is this value, the first scalar. Example here we write is 0 and 0 here, 0 and 0 here. Okay, if we write 0 and 0 here, so this one will become 8 bit and 0 0. Okay, so 0 0 become low significant bit to form a 10 bit. So the timer 2 will count from 0 to CCPR1H here. Okay, so 50% here, if we want 50% of the duty cycle, so 50% of 255 is how much? 50%. So 50% here is will become 178. Okay, 178. Okay, so 178 here we give it to timer 2 here. So we will have the timer 2 as like this. So 178 we can write as a binary like this, 1 0 0 1 0 0 1 0. Okay, and we add 2 more bits here, so this is 0 and 0. So actually this 100, so we will have this 10 bit timer 2 here. Actually we can this number will be 178 multiplied 4. Okay, so it will become 712. Okay, so timer 2, so we will give this number to CCPR1L here. So CCPR1L will be this number, okay, and 0 0 will be the number of the scalar. Okay, so this number will become 712. So when timer 2 increase from 0 to 712 here, the RC2 will go low, and at that time, as I said before, the timer 2 will become 8 bit again, and then the timer 2 will become 178 here, and then it will count up to 255, and then it finishes one loop, and another loop will continue again. Okay, so briefly we will give the PR2 255 to generate the frequency, and the CCPR1L is And this is
178. Okay,
for the calculation of another pic.
Okay.
Another pic. It's similar. It is still similar to our example. So let's read and discuss about this. So when we work with the PWM mode and timer tool, we have to use the registers. This is a lot of register here. Okay, so we can summarize that. If we want to generate the pairs for the PWM signal, we will give the value to the PR2, give the value to PR2 here, and this one, this is a bit signal. Okay, and then we will follow the this equation, this equations, and here we have another value, is the red scale value here. Okay, so we can set the periods of frequency based on the red scale value here. And about the duty cycle, that means this is the high value of the pulse, right here, the pulse here, and this is the duty cycle here, and the duty cycle will be 10 bits. It is the a bit here, and it compiled with 1 bit here and 1 bit here. This is 10 bits, and this is the equation for the duty cycle. This is about the TOSC, right, and the timer to red scale value here, Okay, so this is the example. We want to generate if example here, according to the table. If we use the PR2 value, this is the 255, this one, right, and we use the resolution is the 10 bit value. So and the timer red scaler is 1, so we can generate the frequency here, Okay, and this one is the frequency here, right, and this is the procedure to generate the PWM signal. First we give the pairs to the PR2 register, right, and then we configure the CCP module as the PWM mode, and then we give the value to the CCPR1L and the bit, this one here, 2 bit here, right, and then we start the timer tool, and then we clear the timer tool interrupt, and then we lost the scale for the timer tool red scaler value, and then we start the timer tool, right, and then the PWM signal will output here. Okay, so this is the example of generating the PWM signal. First is we have to define the register address here, right, and the bit address here, and then we generate the periods for PR2 here. We generate the periods. So that means if we use the crystal 20 megahertz, right, 20 megahertz, and if we give the value PR2 is FF, it is 255. So and the press scaler the press scaler of the timer tool will decide by which bit. The press scaler will decide by this 2 bit, right, this 2 bit. So here I said this one is 0.12, right, 12. That mean this one is 12. This means is 0 0 1 0 1 0. So that means this one is 1 0, right? 1 0. So this one will according to the description, if we set this bit is 1, oh sorry, the G2 CON I set here, right? I set here, so that means 0 0. That means the prescaler will be 1, right? And the PR2 is 255, the prescaler is 1, so we want to generate about 19.5 kilohertz. Okay, and the percentage of the high will is this value, right? This value. So we set it is 128. So that means from the calculation we will know that it is 50% high and 50% low. Okay, one. So we give the value to the for the duty value. Okay, and then we set the switch will be 0 to the output, right? And then after this step, the PWM mode will generate. And now after this line, the signal PWM is generated as the pin CCP1. Okay, CCP1. This is pin 16. This is pin 16. Yeah, oh, sorry, this is pin 17 here, and we will see that the LED will bright. Okay, and if you use the compiler CCSC, you just concentrate on 3 functions. The first function is set PWM duty value. This is for the XX here. If we use CCP1, it is 1 here, and the duty value here, and the duty value here is the 10 bit, and another is we set up the timer 2 mode. This one is for the prescaler, right? And this one for the PR2 here, right? Period PR2, and the post scale we use 1 here, right? And this one is we active the PWM mode, right? PWM mode. Here this is the example. Here is the example of the code, right? And please remember that the percentage of the high and the low of the duty cycle is depend on the PR2 value here, right? It depends on the PR2. So if we give the PR2 is 255, if we want the percentage 50% high and 50% low, the value here is this one. And how to calculate this one is according to this function, right? You have to calculate based on this equation. Let's look at this example. This example will show the PWM signal on this pin. Okay, and the duty value is will depend on the analog signal from the resistor here. So that means we can adjust the duty value based on the analog value. So by adjusting the duty cycle of the PWM signal, we can generate the voltage on that pin. Example on this slide, right? if we generate 50% high and 50% low in the output is 5 volts, so the average voltage will be so we can use the PWM mode to control the speed of the DC motor like this. We can make the circuits like this with the MOSFET here, and we can generate the PWM function here, and then we can control the speed of the motor.